friends, so welcome to my channel Symbiosis. So in this lecture I am going to discuss about the variational principle. So this variational principle is used to basically compute the approximate ground state wave function. So in that lecture we will see what is this variational principle. So before the start of my lectures, let me remind you to please subscribe to my channel Symbiosis. So what I am saying that sometimes some system is bit complicated, so in that case it is impossible to get the exact solution of that quantum mechanical system. So if you remember, we have solved the exact solution for hydrogen atom system. So hydrogen atom system is basically one electron system, but there is one nucleus and one electron. But when the system becomes bit complicated, like in case of helium atom, where there is a single nucleus and two electron, in that case we are unable to get the exact solution for that system. So you can see this is the example of that helium atom system, where at the center there is nucleus and there are two electrons, and R1n is the distance between the electron 1 and the nucleus, and R2n is basically the distance between the nucleus and electron 2, and this R12 is basically the distance between these two electrons. Now to solve this system we have to know the Hamiltonian operator for this system, because we have to solve ultimately this Schrodinger's equation, that is H psi 0 is equal to E psi 0. So by solving this Schrodinger's equation we would get the exact energy for that system. So for that we have to know the exact Hamiltonian operator for this system. Now if you see that basically Hamiltonian operator is basically summation of the kinetic energy operator and the potential energy operator term. So these are the kinetic energy term and potential energy term. So these two are basically kinetic energy term, and these three are arises due to the potential energy term. So if you see that generally we can use the separation of variable principle to separate out this Hamiltonian operator into two parts, that is first part that is arises due to the electron 1, and the second part that is arises due to the electron 2. So for all this fourth term we can actually use separation of variable because they are basically separated. But this term creates a problem, because you can see that in that term there is a term that is R12, that is the distance between these two electrons. So this term basically depends on the coordinates of both R1 and R2. So we cannot actually separate this term into two independent terms by using separation of variable. So due to that problem we cannot actually get the exact solution for this types of system. So what is the solution? The best solution to use some kinds of approximation methods like variational principle. So what variational principle actually do, that we will see. So suppose our main target is to determine this psi 0 and E0. Psi 0 is basically the exact ground state wave function for some system, and E0 is the exact ground state energy that is associated with that system. Now this is the equation by which actually we calculate the expectation value of energy for that system. So you can see this is the upper term and this is the denominator part. So you can see that this denominator part arises because sometimes this psi 0 term may not be normalized. So in that case we have to divide this part with this normalization integral. So if this psi 0 is normalized, then this normalization integral will be equal to 1, but if it is not normalized then it has some value, so we have to divide this integral with this constant value to obtain the expectation value or energy. So now suppose that we do not able to get the exact ground state wave function, so in that case we have to take some kinds of trial wave function, or we could say that some kinds of approximated wave function that is expressed as E phi or phi, and the energy that is associated with that trial wave function is equal to E phi. So similar to E0, the E phi will be equal to phi h phi by this normalization integral. So this is basically the Dirac's notation by which we could express the integral. Okay, so what the variational principle says. So now here's the variational principle come into the picture. So according to the variational principle, the energy of any approximated ground state wave function, which is this one, E phi is basically the energy of that approximated ground state wave function. So this E phi will always be greater than or is equal to E0, which is the exact energy of the ground state wave function. So this is the main heading or the main principle of variational principle. Okay, so principle says that if we choose any trial wave function, whatever the trial wave function phi, and if you obtain some energy that is associated with the trial wave function E phi, that will be always greater than or equal to the energy of that exact energy of the ground state wave function. Okay, so suppose that our trial wave function phi is basically depending upon some parameter lambda. Okay, so whatever the value of this parameter lambda it is, the E phi will always be the equal to or greater than E0. Okay, so that is the main thing of the variational principle. So according to the variational principle, we have told you, no matter the value of lambda possess, always this will be true. Okay, so here we will choose basically different values of this parameter lambda value where the energy associated with this function psi is minimum. Okay, so you could see this graph where what we have done, you could see that we have actually changes the value of lambda. So our trial wave function gives different energy values, which is basically depending upon this lambda. So this will give these types of curve. Okay, so by changing this lambda value, our energy of the trial wave function is also changes, and we will get, suppose we will get these types of parabolic curve. So what we have to do, we have to determine the minimum energy. So the points or the value of the lambda at which the energy of the trial wave function is minimum. So in that case, suppose that this is the minimum energy. So this E minimum, whatever we will obtain, will always be greater than or is equal to E0. So we could say that this energy value will be the best possible energy value that we could be able to determine for this types of trial, from this types of trial wave function. So it will be the best representation of the ground state energy for that system. Okay, so suppose we take some example. So here we will see an example of variational principle to determine the best possible approximation wave function and energy of a ground state wave function and ground state energy of a quantum mechanical state, that is called the harmonic oscillator system. So you have already known or gone through this system, and I have given some dedicated lectures on harmonic oscillator system. So if you haven't go through that lecture, you can go back to my previous videos where you will get the detailed lecture about this harmonic oscillator part. So this is the exact solution of the harmonic oscillator that has been already known. So you could see that this psi nx, so this is psi nx is expressed by this. So you could see that there are basically three types of term. So the first term is called the normalization constant, the second term is called the Hermite polynomial part, and the third term is called the Gaussian wave function. Now suppose we have chosen some kinds of trial wave function phi. Okay, so the trial wave function phi is e to the power minus alpha x square. Suppose that our trial wave function is phi is equal to e to the power minus alpha x square. Okay, so here you can see that alpha is the same types of parameter like lambda, that by varying this alpha value we could actually shape or change the wave function of our trial wave function according to our wish. Okay, so this is our trial wave function. Now what will be the Hamiltonian operator for these types of system? So it is basically the summation of the kinetic energy operator and the potential energy operator term. Now this is the kinetic energy term, that is equal to minus h cross square by 2m, where m is the mass of that particle, and into the second derivative with respect to x. So x is basically, I have told you, basically x is nothing but the distortion from the equilibrium position. Okay, so suppose there is a two bonds are bonded by some kinds of fixed bond length r. Okay, so suppose that r equilibrium is the equilibrium bond distance between these two bonds where the energy is minimum. So if this atom is get stretched out, or these two atoms getting compressed, so there will be the change in the bond length. So that change in the bond length is basically expressed by this function x. Okay, so the potential energy that is associated with it will be equal to half kx square, where k is basically nothing but the spring constant. So you can see that our harmonic oscillator, basically the potential energy function for the harmonic oscillator will be looking like this. So as you can see, it has some kinds of parabolic part, so that's why it will look like a parabola. And the wave function, the trial wave function will be look like this. So it will be look like a pure Gaussian shape. Okay, so this is the shape of this trial wave function, and this is the potential energy function that is depending upon the x. So you can see that this alpha term is very important, because this alpha term will decide that whether our wave function is more diffused or more contracted. So that thing will be dictated by this term alpha. Okay, now you could see that the E alpha, that is the expectation value of the energy for that system, or we could also say that is the approximated energy for that system, will be look like this. So you could see that our wave function phi is equal to e to the power minus alpha x square. So at first we have to determine this normalization integral. So this normalization integral is look like this. You could see this is the complex conjugate part. So as this thing is basically real, so its complex conjugate will be this thing only. So the normalization integral will be equal to integral from minus infinity to plus infinity e to the power minus 2 alpha x square. Now if you go through the integral table, then you could actually solve this integral. So the solution of this integral will be equal to root over of pi by 2 alpha. Now we have to determine the upper term. Now as you know that our Hamiltonian operator basically consists of two terms, that is the kinetic energy operator term and the potential energy operator term. So we could actually divide this integral, that is phi h phi, into two parts, that is phi the kinetic energy operator term into phi plus this phi and potential energy operator that is operating on phi. Okay, so we could actually split this term into this two part. So first of all we have to determine this integral. Okay, so and then this integral. Now suppose this integral is like this. So you could see that phi is e to the power minus alpha x square, v potential energy operator is half kx square, and then again phi, this wave function, e to the power alpha x square. Okay, now this will be plus this is minus, this will be a minus term will be there. Okay, so that 1 by k is basically some constant, so it will be taking out from the integral. So the integral will be minus infinity to plus infinity x square into e to the power minus 2 alpha x square. Now again, if you go to the integral table, you could solve this integral. I am not going to discuss about the detail to solve how we could solve this integral, but I will take the final solution, that is equal to half into k into 1 by 4 alpha into pi by 2 alpha. So this is the solution for the potential energy part. Now come to the kinetic energy part. So for kinetic energy, this is the kinetic energy operator minus h cross square by 2m into second derivative with respect to x, that will be operating on e to the power minus alpha x square. So you could actually solve this thing, that is, if you do the second derivative with respect to x for this function, finally you will obtain this thing. Okay, so now you could see that this minus h cross square by 2m is a constant that will be out of this integral, and this 2 alpha part will be also, minus 2 alpha part will be also out of this integral. So the final integral will be minus infinity to plus infinity e to the power minus alpha x square into e to the power minus alpha x square into 1 by minus 2 alpha x square dx. So you could see that this m will be 2 will be cancelled out. So you could see that this integral basically we could split into two parts, that is integral minus infinity to plus infinity e to the power minus 2 alpha x square dx minus 2 alpha, that will be out of this integral. So 2 alpha into x square into e to the power minus 2 alpha x square dx. So this integral, I have already told you, this is the solution for this integral, root over of alpha by 2 pi, and this is the solution for this integral, that is integral in minus infinity to plus infinity x square e to the power minus 2 alpha x square. So the final thing we will obtain, that the final part, that is this one. Okay, now we could actually determine the expectation value, because I have told you that expectation value for the trial wave function phi is equal to like this. So this term I have already determined, this term also I have determined, and this integral also I have determined. So all those terms I have just inserted into this equation, and the final E phi value, that is the energy of the trial wave function, is h cross square into alpha by 2m plus k by 8 alpha. Now I have told you that this phi is our trial wave function. Now this alpha is like a lambda, so I have told you that this we have to choose some trial wave function which will depends on some parameter lambda. So in that case we have to choose that alpha value in such a way that the energy of that trial wave function will be as minimum as possible. So in that way we have to choose the alpha. So what we have to do, we have to take the first derivative with respect to alpha. Okay, so dE phi by d alpha, we have to choose such a point that it will be equal to 0, because that will represent the minima. So if you take the derivative of this, you will obtain minus h cross square by 2m minus k by 8 alpha square is equal to 0. So you could see that for this alpha value, the energy that is associated with this trial wave function will be minimum. So that's why we designate this alpha with alpha minimum. So the alpha minimum is equal to root over of km by 2h cross. So I have told you that the expression for the energy alpha will be like this. So if you put the value of alpha as alpha minimum, you will finally obtain the energy, that is the minimum energy associated with this trial wave function will be look like this: h cross square by 2 root over of k by m. Here I am not going to describe all this mathematical step, because these are simple algebra. You could actually solve it in your own. So this is the energy minimum for that trial wave function, that is equal to h cross by 2 root over of k by m, where k I have told you that it is basically equal to spring constant. Now there is another term that is called omega. So that thing is basically called the angular velocity. So there is a relationship between the angular velocity and the spring constant, that is this one, omega is equal to root over of k by m. So if you just replace this root over of k by m with omega, you will obtain the energy minima for the trial wave function is half h cross omega. So the minimum energy obtained from the trial wave function phi e to the power alpha x square, sorry, the minus alpha x square is equal to half h cross omega. That is the minimum energy associated with this trial wave function. Now we have already know the exact energy for that system, because we could actually solve the harmonic oscillator model system. So this is the energy associated with the nth level for any harmonic oscillator model, where n is basically the vibrational quantum number and the nu is basically the frequency of the vibration. So for ground state wave function, you have to determine the exact ground state energy, you have to simply put n is equal to 0. So E0, that is the energy associated with the ground state for this harmonic oscillator model system, is equal to half h nu. So as you know that there is a relationship between the angular velocity and angular frequency, that is omega is equal to 2 pi nu. So nu is equal to omega by 2 pi. So if you just insert this nu value, you will obtain energy E0 is equal to half h cross omega. So here you could see that this is the exact solution for the harmonic oscillator model, and this is the energy that we have obtained by using our trial wave function. And what we have done by using this trial wave function, whatever the energy that we have obtained from this trial wave function, we have just done the energy minimization. We have so the minimum energy that we have obtained for this trial wave function is equal to this one, and these two are exactly same, we could see. So this is basically according to the variational principle, because if you remember, we have told you that according to the variational principle, E5 will be, that is the energy that is associated with that trial wave function, will be equal to or greater than the exact energy. So in that case, we have seen that E5 is equal to E0. So you could see that by using this variational principle, we could actually determine the exact energy for the ground state of this system. So that is the beauty of this variational principle. Okay. So similarly, if you just this is the trial wave function. So as you know, the value of alpha, that is equal to root over of k into m by 2h cross, that is the wave function that have the minimum energy that is associated with this. So another thing is that this normalization integral is equal to root over of pi by 2 alpha. So because we have seen whatever the trial wave function we have chosen is basically not normalized, so that's why before this wave function we have to multiply with some normalization constant to make this wave function normalizable. So that's why before that alpha we have to divide it with root over of pi by 2 alpha. So that's why this normalization constant arises into e to the power minus km root over of km by 2h cross x square. So this is the wave function, which is basically the, we could also say this is the trial wave function which has the minimum energy associated with it. Okay, so you can see that we could change this value, we could put this value of alpha here, so you will get this normalization constant into e to the power minus root over of km into by 2h cross into x square. Now if you see that the exact wave function for harmonic oscillator for nth energy state is like this. Okay, so this is the normalization constant and this is the Hermite polynomial for n is equal to 0 for ground state wave function is equal to 1. Similarly, if this is the normalization constant for ground state wave function will be like this, 2 to the power 0 into 0 factorial into alpha by pi 1 by 4. Okay, so if you just put this value, you could see that whatever the trial wave function we have obtained is looked exactly the same as the ground state wave function of the exact solution for the harmonic oscillator model system. So we have seen that by using variational principle, we could actually determine the exact energy, or we could also say the energy which is very close to the exact energy of the ground state of any system, which is basically practically impossible to solve. So that's it from the lecture. If you have any doubts regarding this lecture, you could ask me through the comment section, and please subscribe to my channel Chem Biases, and thank you very much for your kind attention. Bye, take care.